The second case in the case of eccentric loading is the stresses in the welded joints in case of bending. So we have a force F is acting on a cantilever which is welded to the gusset plate at the top and at the bottom. So we have fillet weld at the top as well as at the bottom. So let's say we have width is B and D is the depth of the cantilever. If you visualize from this side, we can represent the top weld and the bottom weld. The weld length will be equal to B and they are separated by distance equal to D. And we can visualize the leg size equal to H. Again, to observe the effect of force F on the weld, we have to shift the force to the centroid of the weld group. Now this figure is symmetrical, so you have to just draw two symmetry axes and you can look at the position of center C. Eccentricity will be same as equal to the perpendicular distance from the weld to the force F. This force multiplied by eccentric distance will be the moment. So you have to measure the length along the axis of the cantilever, that will be equal to eccentricity equal to E. So to observe the effect of force on the weld group, you have to shift the force to the centroid position, that equal to F plus one additional bending moment is generated. That bending moment will be clockwise. So the value of bending moment is M is equal to force multiplied by E. So because of the force F, the beam will bend in this fashion and there is a bending stress is developed. The bottom edge will come in compression and the top edge will come in tension. So on this area we can show the tension. Tension will be rightward. So this one will be the bending stress developed on the top edge. On the bottom edge it will act on the leftward side. But actually the failure will taking place due to shear only. So this value of bending stress is equal to M into Y divided by moment of inertia I, where Y to take from the neutral axis. So this axis is same as the neutral axis and this distance will be same as equal to the distance Y. On the top fiber, the distance Y will be same as equal to D by 2. So moment will produce here the bending stress, that will be the equivalent shear stress in a horizontal direction, and the force F will develop the shear stress on the weld area. So let's say we have tau prime is the primary shear stress which is produced by the force F and is uniform over the entire cross section. So we have primary shear stress is due to the shear force F divided by area A. The total area A on the top and bottom will be equal to 2 times the throat thickness multiplied by the length of weld, that equal to B, which is equal to 2 times throat thickness is same as 0.707 multiplied by leg size equal to H multiplied by width is equal to B, is equal to 1.414 times of H multiplied by B. In this fashion we can look at the value of tau prime, and all this value of tau prime will act vertically downward. So all these directions represent here the vertical shear stress due to the force F, which one we are calling as a primary shear. So due to the bending, actually the bending stress is produced, but we know the fillet design is always based on the shear, and therefore we'll say here that the moment M introduce a horizontal shear stress because of a bending stress direction is horizontal, so it will also introduce a horizontal shear stress component in the weld. So we'll represent here the value of double prime as a horizontal component which is due to the moment. So we'll represent here the horizontal component tau double prime. This is the effect due to moment, that is a bending moment. Instead of sigma B, we have to use here tau double prime is same as equal to M. Since we are on the top side, Y is replaced by D by 2 divided by the moment of inertia I. This moment of inertia have to use for weld group. And now from this figure we have tau prime and tau double prime. They are perpendicular to each other. So we can calculate here the maximum value of the shear stress by using the Pythagoras. So we can very well calculate tau prime, that is a primary shear stress is due to the force F divided by area. We have area equal to 1.414 times H multiplied by B, where B is the weld length. And the moment M introduced here horizontal shear stress component, which can be same as our flexure formula. So in this case we have tau double prime is M into D by 2 divided by I. Finally we have horizontal shear and the vertical shear, so we can add these two shear vectorally. So we have resultant shear is equal to tau is the vector sum of primary shear plus the vectors of secondary shear, both quantity in vector form, and you have to use the absolute value of this. But since here they are perpendicular to each other, so we can apply the Pythagoras to find out the magnitude of the resultant shear stress. The horizontal value represent here the secondary shear stress due to bending. Vertical value represent here the primary shear stress due to force F. So this one is value equal to tau. These two are perpendicular to each other. So we can very well apply the Pythagoras and we can find out the resultant value of the shear stress tau. That can be obtained by the Pythagoras theorem. So we have under root of tau prime square plus we have tau double prime square. Only critical part in this one is to calculate the moment of inertia, and finally you have to equate the value of tau with tau max, then you can find out the required force F. Or if the force is known, then we can find out the leg size equal to H. Now we'll discuss here the procedure how to find out the moment of inertia I. Let's consider we have two parallel welds which are vertical. Let's say here this vertical distance is equal to D and the horizontal distance equal to B. Due to symmetry we can locate the centroid here. The coordinate of centroid will be X bar and Y bar is same as equal to C B by 2 and D by 2. B by 2 and D by 2. This one is a centroid. So in this case we have area of the one weld will be equal to 0.707 multiplied by H, that is a leg size, multiplied by D. Since we have two weld here, so you have to multiply by 2. So we'll get this answer close to 1.414 multiplied by H multiplied by D. So this one is the resultant CG through which we are interested to know what is the moment of inertia about the x-axis and y-axis. To explain this, I have just increased the thickness of the weld, but actually it's a very thin weld. For the left hand side we have x1 and y1 are the centroidal axis. This one is x2 and y2 is a centroidal axis. This one is same as our throat thickness equal to t, which will assume to be equal to very small as compared to the length of weld. So value of t is very less as compared to d. The moment of inertia about the centroidal axis Ix is given as B into h cube, that is the breadth multiplied by height cube divided by 12. And moment of inertia of a rectangle about y-axis is given as h into b cube divided by 12. So we have Ix1 and Ix2 is identical value. So we have Ix1 is same as equal to Ix2 is equal to B. B is the breadth is t, into height is d, that is bd cube divided by 12. And we have Iy1 equal to Iy2 is height into breadth cube divided by 12. This time we have height is same as equal to d and the width is equal to t, that is the breadth is equal to t, so we have t cube divided by 12. T cube is very small quantity, so approximately this value we can neglect and we'll make it equal to 0. So we can transfer the moment of inertia Ix1, Ix2 on x-axis. For that one we'll use the parallel axis. The distance between x and x1 is equal to 0. the perpendicular distance between x and x2 is equal to 0. So by parallaxis theorem, we have the moment of inertia about the x-axis is equal to Ix1 plus we have area A1 multiplied by perpendicular distance square plus we have Ix2 plus we have area A2 multiplied by perpendicular distance square. Ix1 is same as Ix2, so we have 2 times of Ix1, and perpendicular distance is 0, so second quantity will be equal to 0. So moment of inertia this time will be equal to Ix1 plus Ix2, that is 2 times. So we have 2 times of t into d cube divided by 12. So this value of Ix is equal to t into d cube divided by 6. So remember this formula when we have the weld are vertical. Now consider here the two horizontal weld. This time we have weld length equal to b and the distance between the two weld equal to d. So basic procedure remains same. You can draw here symmetry line and we can locate the coordinate of centroid. Since I have not changed the dimensions b and d, so we have x coordinate is b by 2 and y coordinate is d by 2. Area of the top weld and bottom weld together will be 2 times. Each weld has an area equal to 0.707 multiplied by the throat thickness, leg size h. Instead of d, this time b will come because we have taken the weld length equal to b. So only change here is that we have to take the proper weld length. In the previous case it was d, now it is equal to b. Now next job is to calculate the moment of inertia about the centroidal axis. To explain the procedure how to find out the moment of inertia, I slightly enlarge the figure. This one is the same as the original center equal to C, that is the centroid. The length of weld equal to B, and these two weld are separated by distance equal to D. And here we'll represent the throat thickness equal to T. The throat thickness T is again a very small value as compared to weld length B. We are interested to know the moment of inertia about the centroidal axis x and y, which is passing through the centroid of the weld group system. Let here C1 represent the centroid of the top weld. This axis is equal to x1. This axis is y1, which is the centroidal axis for the top weld. This one is the second centroid of the bottom weld. This axis is x2. And this axis is y2. x2, y2 are the centroidal axis for bottom weld. Now we want to calculate here the value of Ix1. So we have Ix1 is again same as Ix2. Is given as the breadth into depth cube divided by 12. So we have Ix1 is same as Ix2 is equal to breadth. In this case the breadth is equal to b and the depth is equal to t. Cube of it divided by 12. So we have Ix1 is equal to Ix2 is equal to b into t cube divided by 12. So this quantity of t cube is very small, so we can approximate the value of Ix1 and Ix2 equal to 0. So we have Ix1 is equal to Ix2 is equal to 0. But when we calculate the Iy1 and Iy2, both are identical value because of same size, is given as depth into breadth cube divided by 12. This time we have depth is equal to t, breadth is equal to b, cube of it divided by 12. Now b is a larger value, so you have to consider Iy1 and Iy2. So there is no contribution of Ix1, but only the contribution of Iy, so you have to shape the moment of inertia from y1 to y and y to y2. But y1 and y2, they are on the same vertical line. It means that the perpendicular distance between y and y1, similarly y and y2 is equal to 0. Previously you have to transfer the moment of inertia Ix1 and Ix2 to Ix, because that is a marginal value, and Iy1 and Iy2 is equal to 0. So we have considered here the perpendicular distance between x and x1 and x and x2. All these axes are on the same line, so perpendicular distance equal to 0. So the perpendicular distance between y1 and y2 will be equal to 0. And the perpendicular distance between x and x1, x and x1, and x2 and x, that is x and x2, is same as equal to d by 2, because we have symmetrical figure. So this distance is sufficiently large as compared to the previous case. So we have neglected it in the previous case and we have considered in this case. This time we have area A1 is same as equal to B multiplied by T. This area A2 is equal to B multiplied by T. Now as far as our coordinate system is considered, the centroid, this axis is same as equal to x-axis and this axis is equal to y-axis. If you check this figure here, this axis is same as our x-axis and this axis is our y-axis, and we have bending is taking place about this direction. So this one is a bending moment, that is the bending moment is taking place about the x-axis. So this one is bending moment about the x-axis. So the bending moment is taking place about the x-axis. So I will show the bending moment here equal to m. So I require the value of ix. So only the value of ix is required, and total value of ix is nothing but by parallel axis we have ix1 plus we have area a1 multiplied by perpendicular distance square. Since ix1 and ix2 are identical value, a1 and a2 are also same value, we have to multiply by 2 times. The contribution of ix1 is equal to 0 and even the ix2 is also equal to 0. So we have area a1 is equal to b multiplied by t. B multiplied by t, and we have perpendicular distance square is d square divided by 4 multiplied by 2. So in this case the ix value we required for calculation of the shear stress, that is the bending stress. So we have bending stress is same as equal to secondary shear is equal to m. So this one is mx multiplied by d by 2 divided by ix. So they require the value of ix, and we get this value close to b into t into d square divided by 2. So this value we required for calculation of secondary shear stress, which is same as our bending stress. So we have ix is equal to b into t into d square by 2. A 50 mm diameter and 150 mm long steel bar is subjected to the loading 9 kN indicated as shown in the figure. So the force value is given as 9 kN, the diameter is given as 50 and the length of the rod equal to 150 mm. Force is applied at the free end. Locate and estimate the maximum shear stress in the weld throat if the weld size is 6.5 mm. Weld size h is known, and we have given here the circular weld over the entire circumference. So we have given the force is equal to 9 kN, diameter of the rod is equal to 50 mm, so radius equal to 25, leg size is equal to 6.5, shear stress we have to calculate, and the length L is given. This length L will be equal to 150 mm. So on the given weld, two type of stress is produced. One is the shear stress, that is called as the primary shear due to the force F, and secondly we have the bending stress is produced. Now because of the force F here, the bending moment is produced, and the bending moment is M is given as F multiplied by L. That is the value of F we have to take as 9 and L is equal to 150. So we have 9 which kilo is 10 to the power 3 multiplied by 150 is Newton mm. Bending moment will produce the bending stress, and that is a secondary shear stress, and the force F will produce primary shear stress. Primary shear stress tau prime will act vertically downward and is given as the shear force is equal to F divided by the total weld area, that is equal to F. This area is same as circumference, which is equal to 2 pi r, and we have throat thickness is same as 0.707 multiplied by H. Force we have to use as 9 kilonewton is 9000 Newton divided by 2 pi. The radius of the steel bar is equal to 25 mm multiplied by 0.707 times the leg size H, which is 6.5. This answer will come in megapascal. Is 12.46 megapascal. The polar moment of inertia for a thin ring J is given as 2 pi into r cube into throat thickness, that equal to 0.707 multiplied by H. And the moment of inertia about the x-axis or y-axis is half of the polar moment of inertia, that equal to pi into r cube into 0.707 times H. Because of bending we required here, the moment of inertia, that is the second moment of area, is pi. Radius of the bar is equal to 25, so we have 25 cube into 0.707 and we have leg size H is equal to 6.5. So we have polar moment of inertia is 225581.1 mm to the power 4. The bending moment will produce the bending stress, which we called as the secondary shear stress. We can represent as sigma b maximum, that is the normal stress, or we can call it as tau prime, and you have to use the flexure formula. We have flexure formula is m into y. This time the maximum bending stress will occur at distance equal to r, so we have capital R divided by the moment of inertia equal to I. The bending moment is 9 into 10 to the power 3 into 150. So we have 9 into 10 to the power 3 into 150 multiplied by the value of R. Value of R is 25 divided by moment of inertia, that equal to 225581, 225581.1. This secondary shear stress will act in a horizontal direction. So two stresses will act perpendicular to each other. Is close to 149.6 megapascal. So in this case the tau prime will act vertically downward, tau double prime will act horizontally, both are perpendicular to each other. So we can calculate resultant shear stress by Pythagoras. So we have resultant shear stress tau is equal to under root of tau prime square plus tau double prime square, that is we have under root of tau prime is 12.46, so we have 12.46 square plus we have tau double prime is 149.6 square, is very close to 150.13 megapascal is the resultant shear stress. The video you are watching is from the app, which is the Mohod class app available on Google Store, and in this app we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.